Okay. Victor, what is the first thing I get into? It's probably like some kind of search. Intro. Whoa. No. I didn't know that that was gonna actually go there. Fuck you. Okay, binary search. Big O notation, how memory works, selection, sort, arrays, and linked lists. Recursion, quick sort, hash tables, breadth first. Trees, balanced trees. Dijkstra's algorithm. So greedy. Dynamic programming. K nearest. Where to go next? I see. Go learn more new things. Okay. So I think binary. I'm curious is what will be actually in recursion. Recursion is also a very short section. All right. So I think what we do is have maybe binary search, but I need to just start reading also. So what time is it? 9:08. Let's do at least half an hour. Can I make dirt from here? We'll call it what? Binary search. Oops. Binary search. Not an editor command, because oh wait, I have to do make dir. What's it called? Binary search. Yeah. Okay, so I need to make multiple. I want multiple languages. Also, I need like. Maybe a readme. Oh wait, why didn't that show up? Touch readme.md. What? That's weird. Huh. Interesting. Yeah. Let's do JavaScript. Python. Ruby. Go. I'm gonna skip TypeScript and we're just gonna do JavaScript. Do I want to do anything else? Oh yeah. We're gonna do Lua. Yeah. Not a very strongly typed person, am I? We'll start with JavaScript. And let's just start reading. Let's start reading. Right, my first search algorithm, binary search. I know how to talk about the running time of, yeah, big O. Okay, sure. An algorithm is a set of instructions for accomplishing a task. Every piece of code should be called an algorithm. But this book covers the most interesting bits. I chose the algorithms in this book for inclusion because they're fast, or they solve interesting problems, or both. Here are some highlights. Chapter 1 talks about binary search and shows how an algorithm can speed up your code. In one example, the number of steps needed goes from 4 billion down to 32. Sure. Okay. A GPS device uses graph algorithms, as you'll learn in Chapter 6 and 9, to calculate the shortest route to your destination. Oh, cool. Yeah, I don't know what those are. All right. You can use dynamic programming to write an AI algorithm that plays checkers. Fun. Okay. Describe the algorithm and give you an example. Then I'll talk about the running time of the algorithm in big O. Finally, I'll explore what other types of problems can be solved by the same algorithm. The good news is that an implementation of every algorithm in this book is probably available in your favorite language, so don't have to write each algorithm yourself, but those implementations are useless if you don't understand the trade-offs. In this book, you'll learn compare trade-offs between different algorithms. Should you choose merge, sort, or quick sort? Should you use an array or a list? Just using a different data structure can make a big difference. Sure. What you'll learn about solving problems. You'll learn techniques for solving problems that might have been. So problems aren't solvable in a timely manner. What you'll need to know basic algebra before starting this book. In particular, take this function, f of x, what is the time after 10 reset? Yeah. Additionally, this chapter and this book will be easier to follow if you're familiar with one programming language. All the examples in this book are in Python, so if you don't know any programming languages and want to learn one, choose Python. Okay, sure. Binary search. Suppose you're searching for a person. In the phone book, what an old-fashioned sentence. Haha, it's true. True story. Name starts with a K. You could start at the beginning and keep flipping pages until you get to K's, but you're more likely to start at a page in the middle because you know the K's are going to be at the middle of the phone book. Sure. Suppose you're searching for a word in a dictionary and it starts with an O. Again, you'll start near the middle. Now, suppose you log into Facebook. When you do, Facebook has to verify that you have an account on the site, so it needs to search for your username in the database. Suppose your username is Carl Megd. Okay. Facebook could start from the A's. Okay. So I see. Yeah. This is a search problem. All these cases use the same algorithm to solve the problem. Binary search. Binary search is an algorithm. Its input is a sorted list of items. I'll explain later why it needs to be sorted. Well, sure. Totally makes sense, 100%. If it was not sorted, then you couldn't jump to like the middle. So let me see. If an element you're looking for is in that list, binary search returns the position where it's located. Otherwise, binary search returns null. So my guess is like you kind of like jump to the middle, and Or you jump, yeah, you like, I bet you like divide it by 2. And then, yeah, it's gonna be like this, right? It's gonna be like, I'm gonna have ordered lists. 6, 7. Oh my god, yeah, thank you. Require binary search. What? How dare you? An ordered list, right? Sure. No, I don't want you to. No, go away. Get out of here. I'm doing this myself, Copilot. No, get out of here. No, get out. I'm gonna have to turn you off for this. Ask Copilot. No, I don't want to ask Copilot anything. Copilot disable. Disable. Okay. Cool. Which takes a list and a target. Target. So it gave me a hint there. I'm guessing I'm gonna do like ordered list divided by 2, like length divided by 2. Should be 10. Oh, 5. Right? 2, 3. And so we'll be like ordered list at 2, and we want to find, what we're trying to find is like find like the 8. So you go at ordered list 5, which should give you 5. Which should just give you 5. And then it's going to be like, is 5 less than 8? And you'll say, yeah. So go right. So I've definitely done this before in my life. I've just never called it binary search. Just, I mean, is it here? Less than the target, so we're gonna go this way, and then we're gonna take these, so we'll have 5 items, and then you go to the third, and you like round up, and it'll be like, so then we'll have an array of like 6, so then we'll have like R is equal to like the ordered order. I'm gonna go ahead and just call this OL. We all know what it is. It's like OL slice at 5. Oh, I got an Indian array slice. Do I have my Jiminy's? Do I have my Jiminy's in a row? 2. You got camel duck. 0, 1. You start at 2. Yeah, it's inclusive, not exclusive. So you'd slice at 1, 2, 3, 4, 5, but it's inclusive. So then that should give you like so that gives you an array of like 6, 7, 8, 9, 10. And then you do like R divided by 2. And you take like is it seal? Is it seal or is it floor? I think it's Does that work again? Wow. Good thing I'm doing this because I feel rusty as fuck. 1, 2, 3. Let's go with 4. No, let's go with 3. Length divided by 2. But we do this. Seal. Math seal. Is it math seal? Yeah, and then it's like math. Or would give me 1. Yeah. So we do like math.seal at the array divided by 2. Yeah. Math.seal. And then we would say, does that equal 8? And we'd say, yeah. We'd say, yes, queen. And we'd be correct. Otherwise, you keep going down. So you could do recursion. Could just loop. All right, that's to complete. I'm guessing. I'm guessing that's what we do. All right. So if the element you're looking for is in that list, binary search returns the position where it's located. Otherwise, binary search returns null. Okay, here's an example. Kramerica Industries is in the phone book, entry number 1440. Vandalay Industries, null. Looking for companies in a phone book with binary search. Vandalay Industries is not in the phone book. Now here's an example of how binary search works. I'm thinking of a number between 1 and 100. You have to try to guess my number in the fewest tries possible. With every guess, I'll tell you if your guess is too low to try or correct. Yep. Did it. I did it. Because you got to go left or right, or you're dead, or you're done. Suppose you start guessing 1, 2, 3, 4. Too low, blah, 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 blah. Too low. Oh, he's like, oh, shit. Help me. Well, sorry. Saw a bunch of chats. Whoa, midnight raid. Oh, hello. I'm not a normal... I don't stream a lot. So I just turned over and saw my chat and was like, what are all these people? Usually it's just weird little bots showing up. Or people wanting to, like, try and make me, graphics. It is not a Ring rooftop camera. It's just really high up. Because I like to do one monitor and I usually stand. Why are you studying algorithms? Mostly trying to just hone my chops. And I've never actually studied algorithms because I'm all self-taught. And I've been doing web development stuff for a while now. And I never actually did this stuff. Whoa, how many people are here? What the hell? 58 people. Oh, okay. Thanks for the raid. Raided. Alright. We are mostly real people. I believe you. I believe you. Yeah, I'm studying because if I get into an interview at some point that I need to pass through some of this kind of stuff, then I can actually speak to it. Yeah, I just grabbed this guy's book, Grokking Algorithms, and decided to give it a shot. I just finished a different one, like systems interviews, and it was okay. But I wanted to have a little bit more fun, and I do a lot of TypeScript development, and I do a lot of Ruby stuff these days, and I'm starting to learn Go. So I wanted to poke my head more in the Go space, and then there's a bunch of Python stuff out there right now. I've done LeetCode before, but and I probably will do more. I don't know. I like longer form stuff sometimes, and I wanted to actually like go through some kind of stuff. And this book seemed fun to go through. Okay, so of course this dude hates his life, trying to get through. Better way to search. Did I guess it right? So here's a better technique, starting with 50, right? You divided it by 2, and it's gonna go left or right, right? It's too low, but now you've eliminated half the numbers. Yeah, so no, that 1 through 50 is too low. Next guess is too high. You keep going until you get it in 7 steps. Okay, simple search. How many steps binary search? Simple search could take 240,000. It seems like all the books on algorithms are bad. I have no idea. This is my first one ever. Literally just started like 10 minutes ago. Or wait, more than 10 minutes ago. So I don't know. We'll see. Yes, it is a book on algorithms. It's called Grokking Algorithms. This one's licensed to me. Manning gives you, if you buy it, Manning will give you like the free like PDF version. So I got it right here. LeetCode is a W. We're all crazy LeetCoders. Oh, okay. Cool. I've done some LeetCode for sure. I've definitely played around with it. I haven't logged on in a while, but I figured I would do some. Mostly I wanted to work out a bunch of stuff, and decided I would do like where am I? Man, I've been not using GitHub in a long time. I've been using a lot of GitLab. So I'm starting this Palgorithms repo where I'm gonna, oh, I didn't push up anything. Yeah, where I'm just gonna do, I don't know, this is what I was thought. I just kind of follow the book, do binary search, and like do that in these languages and kind of keep moving on. LeetCode daily problem. Libgen. I don't know what Libgen is. I'll look it up. Libgen. R, okay. Library Genius? I don't think this is the one. This is probably not the one. Right? Yeah, I'll check out the Library Geniuses. See for 80 million scientific articles. Okay, maybe this is a thing. Yeah, I will check out the LeetCode daily. For right now, I really just wanted to keep working through, or at least give this a shot. Read this book and kind of go from there. I'll search books on that site. Cool. Oh, okay. I'll bookmark it. Libgen. Is this the right thing? Download. Get some fiction going. Okay, here we go. Bunch of stuff. Whoa. Computers, algorithms and data structures. Nice. Cool. Whoa. Nice. Sweet. I'll check it out. Just search on the book site. Cool, yeah. I'll check it out. Thanks. Yeah. And I'll probably play around with LeetCode again. Not much. Like, definitely enough. I'd want to spend not as much time on algorithm work as I would in wanting to dive more into a couple other things, like Event Store. If any of you has anyone ever played with Event Store? I really want to play with Event Store. Oh god. LeetCode problem? You? Are you all just a bunch of LeetCode nerds, like you said? Isomorphic strings. LeetCode and chill. Sure, okay. Nice, cool. Well, thanks for stopping by, everybody. Appreciate it. I think this is actually the only time I've ever had people come in and actually hang. So I'm gonna keep going. I'm gonna keep going on this a little bit and kind of work through it. See where we get. All right. Simple search took the 240K. If the word you're looking for is the very last one in the book, you cut the numbers in half. Sure. So binary search will take 18 steps. Big diff. In general, for any list of n, binary search will take log to n steps to run in the worst case, whereas simple search will take n steps. Logarithms. Which data structures one? You mean like Manning has a few good ones? Grokking data structures. You know, I noticed that they have a bunch of grokking ones. Yeah. Just tonight, I noticed there was a bunch of them. I'll check it out. Thanks. Yeah, the event store thing. I'll get back to the binary search in just a second, but oh man, they need some help. You can't read this for shit. You can't read this at all. Wow, it's terrible. Event store seems pretty neat, but I'm a pretty big nerd for event-driven stuff, and I'm a big fan of CQRS type things and Kafka type stuff, different like solutions in that space. An event store seems like a neat alternative. I just don't ever have the time to actually play with it. So I am going to spend some time doing algorithms, but at some point I'd like to dive more into this product and like really check it out. It seems like it has some actually neat stuff going on. Okay, logarithms. I will grok these nuts. It's gonna happen. You may not remember what logarithms are. Sure. You probably know what they're special. Logs 100 asking. How many 10s do we multiply to get 100? The answer is 2. Log 10, 100 is 2. Logs are the inverse of exponentials. Wow. Yep, Big O, sure. I do know Big O a little bit. I'm a real big noob with Big O, but like I get it. It's like runtime speed. of your algorithm. How long it takes to try to like crunch through something. And you don't want it going like this. You want it going like that. Yeah. How it scales. Yeah, see, this is the reason why I bought the book, and I'm learning. I'm trying to get all the right words, so when I get into an interview, I don't go. It doesn't go like this. It goes like this. That's what you go for. Instant denial with that kind of language. When you search for an element using simple search, in the worst case, you might look at every single element. Sure. So for worst case, look at everything. Yeah, that makes sense. So for a list of 8 numbers, you have to check 8 numbers at most. Binary search, you have to check log in elements. Worst case, list of 8 elements, logging is 3. 8 numbers, you have to check the numbers at most. 3 numbers at most. Okay. I'll talk about log a lot, so I should understand them. Okay. I'll probably have to go do that again. I'll have to go look at that again because it's been a long time since I've been around that kind of stuff. Only works when it's a sorted order. Already makes sense. For example, blah. I get that. Let's see how we write it in Python. Okay. Low 0, high length. All right. This will be fun because I don't really know Python very well, like at all. Sometimes I help others with their Python, even though I don't know it. But we make it happen. This code sample here uses arrays. Okay. If you don't know how arrays work, don't worry. Okay, sure. You just need to know that you can store a sequence of elements. Okay. Consecutive buckets called an array. All right. I see. This is like really dumbed down for sure. Okay. It's fine. It's good. Buckets are numbered starting with 0 first. Okay, sure. Okay, sure. Okay. Or we're making a binary search function. Cool. Okay. Mid is the low plus high. Each time you check the middle element, mid is rounded down by Python automatically. Okay, so like I was working out doing like a seal or like a floor. If the guess is too low, update low accordingly. If the guess is lower than the item, you update low. If the guess is too high, you update high. Sure. While the low is less than. Whoa, look at these arrows. What is happening? Look at all this. Double slash is integer division in Python. Result is truncated. Yeah. Like, so like, I'm gonna do some JavaScript to start all it off with, and it's like, whoa. Well, obviously it's not that, but it's like this, where it's gonna do. So instead of 3 like that, it's. But it's going floor. So it's doing like this. So instead of 1.5, you're getting the 1, right? I mean, in Python, that's what the double slash is doing. I totally read it wrong. I read this as a comment. Nice. Okay. I rounded down by Python automatically. Got it. Check. I'm a Python noob, so yeah, it works out. Okay, cool. I definitely thought this was just a comment. I was like, okay, low plus high. Cool. Moving on. If the guess is lower than an item, low is equal to mid plus 1. We start at the beginning and we go to the end. Okay, go to the length -1. Sure. Low and high, keep track of which part of the list you'll search in. If you're going like left or right or low or high, sure. While you haven't narrowed it down to one element, sure. Less than or equal to high. That makes sense because once they meet, then you've found your item. And you check the middle element. Yeah. And your guess is at that mid. That's right here. This is what I was guessing we would do. Get out of here. Like this right here. You'd guess. You take your guess at like the half point. Yeah, and then if your guess is equal, you found it. Yep, I had that too. Where like you're equal. I did like, yeah, I was like looking for 8, divided it, did a floor. I can't remember. We rounded, and we would have been equal to, and so we would have been good to go. Otherwise, if you're lower than, okay, if your guess is higher than the item. Wait, where's item again? Oh, we're getting it passed in. Oh, is this doing recursion? No. No. Oh, it's just the item I'm looking for, like a number. Yeah. If the guess is higher than the item I'm looking for, then I go mid -1 because the guess was too high. Yeah, sure. Or because you're changing your mid? Oh, you changed the low. You changed the high and the low. Okay, yeah, I get it. You keep. Yeah. Okay, cool. Thanks. The hash or like pound or whatever is for comments in Python. I'll write Python at some point. I don't. It's like .py. Did you use indexes? Did you use main.py? Is that your deal? This is a comment. Do I even have I should have. Oh my god, I never run. I had, yeah, there we go. I don't even know how to run this. Python 3. What is this? Where am I? Binary search Python. Sure. And then what? Main.py. I don't know. Would you do like Python? Whoa. Python read main.py. Oh shit. Is it, do you use print? Hi mom. Hi stream. Thanks for raid. Is this how you do it? Am I Pythoning? Oh. Nice. I did it. Alright. So we have to move our high and our low. Guess is greater than the item. So our mid. Hold on. Now my brain is actually having to work a tiny bit. Even though it already all makes sense, like now I'm like having to map it out. So we're changing our high. No, yeah, we're changing highest to mid. So we divide it by 2, mid -1. Because we want to go, because we were too high, we want to go to the left. We want to go lower, and we're in an ordered set from like low to high in this scenario. So we change where our high is. Yeah, it makes sense. And you don't change your low, right? Yeah. You don't change your low. Oh, okay. And this is some Python like. indentation stuff happening. Oh, do you not end your functions? Do you not have like an end in Python? Like, hold on. Sure. Oh, okay. Is that real? No. Do I do this? Yeah. Okay. Okay. I would take getting used to. That would take. That's gonna take some good. That takes some getting used to. But it makes sense. Yeah. I don't think I ever deal with that. I write a lot of TypeScript. I've been writing a lot of Ruby. I was doing some Lua. I started on my Go journey, which I still haven't really touched on too much. None of those use that. I write a fair bit of YAML, but it doesn't really matter. Doesn't really. Okay, cool. So you do indentations. Got it. It's indentation based. Oh, do I have already? Let's see. Whoa, you're gonna give me the juice? Expected. Okay. Pylance. So this is an LSP that was already probably like built in. It's to VS Code, which is how it's getting that. Do I already have formatting? No. Install formatter. Does prettier not work? Probably not. Maybe. What do you all use in, since it sounds like you got some Python people here, what do you all use for or like for formatting with Python? Does Python itself just have like a built-in formatter? Correct Python indentation, 8.7 million. Okay. Whatever. Can I just do this? That's fine. Okay, I think this is making sense though. Like if I guess, I'm gonna return none. Is none a real thing in Python? Okay, that must be some kind of like null value. Just none. That's a new one. Yeah, I got it. Some people use some people use black. So here, let's do some JavaScript stuff. Copilot, go away. No, just go away completely. Function binary search. Sure. So what? A list and are they using target? Item. Sure, let's use the item. Whatever. And then some ordered list. Oh, see, this is where you want Copilot. Sometimes. 6, 7, 8, 9, 10. Sure. Oh, I already had the exact same thing up there. Whoops. All right. So I have a low and a high. Let's see if I can get it without looking back at the thing. All right. So we could do a while. That's fine. Was it while the low is less than the high? Less than or equal to? Whoops. If I gotta get mid. That was like a math 4, I think we wanted to do. Greatest. I guess it doesn't really matter. You just need like a rounding either way. So, oh wait, so now I want to divide. So this starts at 0, and this starts at the list length -1. I think. And then it would be is it just the height? Just be the height. Binary search doesn't return the item, it returns the location of the item, I think is what I'm understanding. Whatever. For right now, I'll just return item. If the high was higher than the item, I'll say my high is mid -1. The high was at, it's going to be over there at numero 10. My first guess is going to be at like 5. If I'm let's say I'm looking for 8. it's going to be too low. Doesn't feel right yet. It's something like this. Hold on, that doesn't feel right. If the low is less than... yeah, see, my brain is actually having to put it in these terms I don't normally do. Okay. All right. This is our guess, right? Mid is our guess. I'm going to divide by 2 and say, is this my item? I'll say, yes, it is. Go for it. Otherwise, do I have to say, is mid higher than my item? Well, because I need to know if I need to go left or right. So 5 is going to be less than where I'm at. I need to include the load in the check because the low is going to change. Oh, yeah. Right. Which is what I had done up here in my pseudo. Whoops. I had kind of like I didn't calculate the high and low at all, but I knew that I had to get the item. So 10 minus 0, 10 divided by 2. So you have to like subtract the low. Maybe that's it. I could say guess. I could say guess is going to be the list at mid. And I could say if guess is equal to item, then return the guess, I suppose. Maybe. This seems like it needs to not be necessary. Is it my high? Yeah, because my high will be changing. If my high was greater than the item, don't change the mid though. Oh no, I'm not changing mid here. I'm saying, well, it's my mid minus 1. But I want my high to go. My high was past the mark. Oh, let's see. My high was past the mark. It's starting to come together. You're close. Yay! Thanks. If my high... So in this example, I should get, my first guess should be 5, which is going to be too low. And the high is not going to be greater. Or is it going to be greater? Let me think about this a little bit more. My low let's see, if I'm here, right, I want to get to like here or here. So it's kind of like if it's the high was greater than the item, I almost like don't want to change it. Yeah, this seems like I'm doing something funky here. In my scenario, I'm pretty sure what I want to do is I want to leave my high where it was. And I want my low to come up. I want my low to be like the mid +1. And it's maybe not like my high, it's like my high was greater than like my guess almost. It's kind of like that. If the high was greater than what the guess was, this seems wrong. All right, I'm gonna go peek at the thing and make sense of it, because that's what we're doing here. I have guess equal. Whoops. Did I close down my stuff? Hello? Oh, I have it in Zen mode. Duh, that's right. All right, yeah, right. Now, if the guess is greater than the item, okay. If my guess was greater than the item, all right. Let me. So I had that wrong. I knew that if it felt wrong. Okay, let me just ponder that for a second. All right. I'm looking for the item. Here was my guess. My guess was greater, which is not going to be true. It's going to be my guess. Oops. My guess is going to have been lower than the item. And I want my lower to come up. So like my low is now mid, let's say ++. This might be it. This is potentially it. So whoa. Okay, let's do binary search. My list, and we'll look for 8. I'm missing if I don't ever find it. So I'll need that. And I can do that outside of the while. It would have returned undefined eventually, but we'll return null. That's fine. Whoop. Oh, whoops. I did something dumb. Oh, did I assign a const? Oh, I see. Oh, shoot. It. Whoops. Okay. That also might be improper. I might not want to do a minus or a plus on that. Oh no. That's a no, cancel that shit. I got my loop. My loop is wrong. That should have exited like super quick. And it wasn't, so less than or greater to my high. The guess is lower. Yes. That makes sense. The search is, if it's lower, you want to move it to the right. Yep. Okay. So good question. How can I change the bounds to alter the search area? Which I believe I have done. But I do think I've got something wrong right here. Possibly. We're gonna peek. Oh, they actually have a less. Oh, they did. Let me think about this. I may have screwed this up. They added them, not subtracted them. How does that change for me? So on my second iteration, the low is going to change from a 0 up to a 6. I think. And that's what I want. And looping. Let's just do what they did and then I'll make sense of it. Okay. Looping. Hadouken. Now if I bring that back and run, do I get myself tied in knots? Oh yeah, there it was. Yeah. My computer's taking off. Okay. So I think that's right. So function like gen lists. Let's take like a upper bound or sure. And say let's do a 4. I have a little list? Yeah. Hooray. Okay. So now okay, so now I've got 10,000 items. And I want to look for 1, 2, 3, 4. And I don't want to log this out. Bam. I'm returning the actual item itself and not the location. And this is 1, 2, 3, 4. So it's gonna be, should be at the 1,235th spot, I think. Let's return the guess and the mid. Oh. Oh, 0, 0, right. Okay, never mind. Duh. Yeah. Cool. Well, I think this is a great start. I'll probably need to have more other little generators or some crap. So let's do, actually, I want to just do a little bit of a, I don't remember what the JavaScript find algorithm is. Like the, what is it, C++? Whatever JavaScript actually gets executed in, I can't remember. Like boiled down to. The algorithm in the array find method is supposed to be actually be really good. Last I checked. And so I would guess that this versus a find itself, as far as execution time is concerned, I probably don't see much of a difference. Whoops. Oh, that does not do jack shit. How does this work again? You have to open up time and then you have to end it at some point, and you can log in between. So this starts it, and then you have to say end, I think. Time end. I think that's how that works. Yeah, okay. So then let's look for 4, 3, 2, 1. So that should be, it should be how long roughly that's executing on. And so I wonder if then I just said l.find 4, 3, 2, 1. I mean, this is not a great. This is not a good test really at all, but I want to see what happens. Oh, I'll just die. Oh, I'm probably not using that right at all. Fine. Oh, I have to do the predicate and the value and the index value. Oh, find is the wrong method that I was looking for. Yes, actually, find is the wrong method. No, it's the no. That's right. I was just thinking about something incorrect. So x is an x is equal to 4321. Should be that. Can I, does this let me label? Does this let me label? No. Or maybe? It does let me label. So, we'll call this binary. And I can't remember what the algorithm is that actually runs find. Okay, so now let's do something. We're at 10,000, 100. All right, here's a million. We'll throw a 0 onto these suckers. Yeah, you see that? This shit's apparently faster. That's curious. Wow. Does it? It might. Does it have a weird name? I remember it being named something weird like Eric's algorithm or something weird, something funky. Oh my god, I'm such a Twitch noob. I have no idea how many people are here. I guess I'd have to like log into mine. Underlying algorithm or JavaScript array find. I'm curious. I'm even more curious now. V8 developer here. No big deal. Binary search. Oh, interesting. When was this? In 22? Highly optimized engine may be able to make your O encode somewhere between 10% and 10x fast otherwise would be. Switching to an O log n or O1 solution on your end, you can speed it up by orders of magnitude. It's often accomplished by doing something that engines can't possibly do. For example, you can keep your array sorted and then use binary search over it. That's something an engine can't do for you automatically because it's obviously not allowed to reorder your array's contents without your approval. Okay. Interesting. Cool. All right, exercises. We exercised. We're fully exercised at this point. Suppose you double the size. Oh, it's been doubled. Running time. Okay. Anytime I talk about an algorithm, I'll discuss its running time. Generally, you want to choose the most efficient algorithm, whether you're trying to optimize for time or for space. Back to binary search. How much time do you save by using it? Well, actually, orders of magnitude. Look at that. First person check each number one by one. It's 100 numbers, 600 guesses. It's a list of 4 billion numbers. It takes up to 4 billion guesses. Oh man. This is actually a valid JavaScript. I think. I usually don't use it, but I believe it's real now. Oh, invalid array length. Okay. Let's try again. Oh, I did not like that. Too high. Okay. Too high. Really? Boom. Okay, anyways. If it's a list of 4 billion numbers, it takes up to 4 billion guesses. So the maximum number of guesses is the same size as the list. That's called linear time, which is what we were just kind of touching on in chat. Binary search is different. If the list is 100 items long, it takes at most 7 guesses. If the list is 4 billion items, it takes at most 32 guesses. Powerful, eh? Seems like it. Binary search runs in logarithmic time, or log time, as most people call it. Here's a table summarizing our findings today. Simple. 100 items, 100 guesses. O of n, linear time. O log n, logarithmic time. Okay. Now over to some big O chattings. Big O notation is special notation that tells you how fast an algorithm is. Who cares? Well, probably lots of people. Well, it turns out that you'll use other people's algorithms often, and when you do, it's nice to understand how fast or slow they are in this section. I'll explain what big O notation is and give you a list of the most common running times for algorithms using it. Algorithm running times grow at different rates. Sure. Bob is writing a search algorithm for NASA. His algorithm will kick in when a rocket is about to land on the moon. It'll help calculate where to land. Okay. This is an example of how the runtime of two algorithms can grow at different rates. Bob is trying to decide between simple search and binary search. We know Bob's got to go binary, right? The algorithm needs to be both fast and correct. On one hand, binary search is faster, and Bob has only 10 seconds to figure out where they land. Oh. Otherwise, the rocket will be off course. On the other hand, simple search is easier to write, and there is less chance of bugs being introduced. Bob really doesn't want bugs in code to land a rocket. To be careful, Bob decides to time both algorithms with the list of functions. All right. Yeah, okay. I see that there will be some parts of this book I'll probably just kind of have to skim like over a little bit. But that's fine. It's fun. Let's assume it takes 1 millisecond to check one item. With simple search, Bob has to check 100 elements. Search takes 100 milliseconds to run. Log 2. Wait, let's see. On the other hand, he only has to check 7 elements with binary search. Log 2 100 is roughly 7, so that search takes 7 milliseconds to run. But realistically, the list will have more like 1 billion elements. If it does, how long will simple search take? 1 billion. 1 billion milliseconds. And how long will the answer both? Right. Simple search or linear search. It's like 1-to-1, so it's going to be like 1 billion. What was it supposed to say? It takes 100 milliseconds to run 100 elements. So it's 1 billion milliseconds, sure. And as far as the like binary search time or the logarithmic time, off the top of my head, I have no idea. Smaller. Bob runs binary search with 1 billion elements and it takes 30 milliseconds. Because a log 2 of 1 billion is roughly 30. 30 milliseconds, he thinks. Binary search is about 50 times faster than simple search because simple search took 100 milliseconds with 100 elements. Binary search took 7 milliseconds, so simple search will take. Okay, I see what they're doing. Said Bob up. Nope, Bob. Turns out Bob was wrong. Oh, Bob. Dead wrong because Bob's dead. Bob couldn't land on the moon. He chose simple search. Oh, no. The runtime for simple search with 1 billion items will be 1 billion milliseconds, which is 11 days. Whoa. The problem is, and he only had 10 seconds. Bob, you silly dumb fuck. The problem is that the runtime for binary search and simple search don't grow at the same rate. Sure. So we're talking about growth. Whoop. Runtimes grow at very different speeds. The runtimes grow at different speeds. Sure. As the number of items increases, binary search takes a little more time to run. Sure, but simple search takes a lot more time to run. So as the list of numbers gets bigger, binary search suddenly becomes a lot faster than simple search. Sure. Bob thought binary was okay. That's where big O notation comes in. You need to know how the running time increases as the list size increases. So like time and space. Thank you very much for stopping by. Appreciated the help. Yeah, it was fun to hang out with people in chat while I'm doing something new. So I'll catch you later. Big O notation tells you how fast an algorithm is. For example, suppose you have a list of size n. How fast an algorithm is, sure. Simple search needs to check each element, so it will take n operations. The runtime is O of n. Okay. What are the good ones? I can't. So big O notation. I know. Yeah, I've seen this graph before. A bunch. Interesting. So you want to be in the like O log n, which is what binary search is, or O of 1. You like strive for those according to this random internet picture. The runtime in big O notation is ON. Where are the seconds? There are none. Big O doesn't tell you the speed in seconds. Big O notation lets you compare the number of operations. Okay. The number of operations, that makes a lot of sense. It tells you how fast the algorithm grows. Okay. The number of operations. Okay. Binary search needs log n operations to check a list of size n. Binary search needs log n operations. Okay. To check a list of size n. What's the running time in big O notation? It's O of log n. In general, big O notation is written as follows. The big O, it's operations. Does O stand for operations? It must. Did it already say that? Nope. That seems to be what it should stand for. Figure out the runtime for these algorithms. Now let's look at some examples. Visualizing different big O runtimes. Practical example of what you can follow. Draw 16 boxes, one at a time. Remember, big O notation counts the number of operations. In this example, drawing one box is one operation. You have to draw 16 boxes. How many operations will it take? Okay. I mean, I really appreciate this, but I'm pretty sure I mostly get the basic idea. It's how many operations grow depending on like the size of your input. Like greater input, then how many like operations does that lead to, and like large and like how that compares. Like what does the growth look like? Yeah, that makes sense. Because if I think linear, I'm thinking just like a linear line on the graph. Yeah, like this little bitch right here. That thing. Oops. Okay. Big O establishes a worst case runtime. Suppose you're using simple search to look for a person in the phone book. You know that simple search takes ON time to run, which means in the worst case, you'll have to look through every single entry in your phone book. In this case, you're looking for edit. The guy is the first entry in your phone book, so you didn't have to look at every entry you found on the first try. Did this algorithm take ON time, or did it take O1 time because you found the person on the first try? Okay, sure, it's still ON. Makes sense in this case. You found what you were looking for instantly, but that's just a best case scenario. But they're going for a worst case scenario, so it's the item going to be at the end, which is why in a simple search or in a linear search, it's going to be an ON and yeah, okay. Entry the phone book. That's ON time. It's reassurance. You know, simple search will be slower than ON. Some common times. Log in, also known as log time. Example, binary search. log in, I mean, in linear time, simple search. In times log n, a fast sorting algorithm like quicksort. That'll be fun. I have never implemented quicksort. I also don't even know what quicksort really is, so that'll be fun. In squared, example, a slow sorting algorithm like selection sort. Okay. A really slow algorithm like the traveling salesperson. Coming up next, isn't it? Suppose you're drawing a grid of 16 boxes and you choose from 5 different algorithms to do so. If you choose the first algorithm, make a particular log n times draw the grid. 10 operations. Okay, yeah, sure. Slow. Alright, so log of n, otherwise known as log time. That's our friend. This is our friend here. Algorithm speed. It's not measured in seconds, but the growth of the number of operations. Yes, growth in number of operations. Instead of seconds, we will talk about how quickly the runtime of an algorithm increases as the size of the input increases. Yeah, that made a lot of sense. Runtime of algorithms expressed in big O notation, sure. Log in is faster than ON, and it gets a lot faster as the list of items you're searching grows. Exercises. Give the runtime for each of these scenarios in terms of big O. Okay. I hope there's an answer section, because I don't know. If you have a name and you want to find a person's phone number in the phone book. Okay. It's a phone book, so I can assume it's a sorted set. Sorted by their name. We won't know exactly where it is in the book, so we will have to do a find for it. We can do a binary search. So I suppose this one would be O log n. Moving forward, you have a phone number and you want to find a person's name in the phone book. Hint, you have to search through the whole book. Yeah, yeah, it sounds, yeah. So it's not going to be sorted by phone number. You have to look through and just check every single one. I will just guess it's O of n. That's my first guess. You want to read the numbers of every person in the book. O of n. You want to read the numbers of just the A's. This is a tricky one. Read the answer, you may be surprised. Okay, all right. Answers must be lower. So I said O of log n for the first one. I said O of n for the next one. I said O of n. It's O of n definitely for 1.5. You want to read the numbers of just the A's. Well, that's still O of n, because you don't know how many A's there are, and it's just worst case scenario. So 1.5 and 1.6 are O of n. I think 1.4 is O of n. 1.3 is log n. Alright, traveling salesperson. But I mean, I want to read through all this, but I want the answers. Where are the answers? Are they in the back of the book? They might be. Check the actual book. I found the answers. Okay. We've got answers. Let's see where I was at. Okay, 1.3. I said O log n. Answer, O log n. Nailed it. 1.4. I said O of n. Answer is O of n. Nailed it. I said O of n for all of these, and it's O of n. I got it right. 100%. I've passed the class. I can retire. Okay. That's all for me tonight. Don't know if anyone else is still watching, but thanks for hanging out. Appreciate it. I'm gonna call it. I will continue this journey. We'll be writing more code, doing all these algorithms in various languages. It'll be a good time. Thank you for the raid. Thanks for hanging out. See ya.